Yo, what's good, everybody? Having a late night session. Okay, so this isn't targeted to my high school students, but more towards maybe a college student taking an intro to proof-based math course or a discrete math course, right? Or just anyone interested in higher level math and just seeing how how the math works. Okay. Okay, cool. So here we're going to prove that the square root of 2 is irrational using a proof technique called proof by contradiction. And we are going to assume the opposite, right? That instead of square root of 2 being irrational, that it is rational. And then using this assumption, we are going to get, from the logical steps, other statements that are true. And then you're going to get to a point where you're going to get a statement P happens, and then dot, 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 not P happens. So essentially, the contradiction is this, P and not P, and you know that this can't happen, okay? This cannot happen, okay? Cool. All right, great. So I wrote a little bit here. That's not my first take. All right, but anyways, yeah, so here, assume the contrary, that the square root of 2 is rational. So by definition of rational, this means that there exists two integers such that square root of 2 can be re-expressed as a ratio of those, okay? So you could say square root of 2 is equal to a over b for some a, b, and z. And you can also assume that b is not 0, okay? It can't be 0, because otherwise this would be undefined, okay? And we can also assume, okay, that a and b have no common factors, okay? Another way of saying that is you could say that a and b are co-prime, okay? So that they have no other common factors other than 1, okay? Have no common factors. I mentioned this because this is actually the statement that we are going to contradict, okay? And you can make this assumption because anytime you have a fraction, right, that's not in simplest form, you can reduce it. So basically what I'm trying to say here is that A and B, they are, it's like the most simplest case, okay? We could talk about equivalence classes and all that stuff, but yeah, okay, right here, okay. Yeah, so here square root of 2 is equal to a over b, and then this implies that when you square both sides, that 2 is equal to a squared over b squared, right? Which implies that after multiplying both sides of this equation by b squared, that 2b squared is equal to a squared. And then this equation can be interpreted in multiple ways. But if you look at this carefully, one way of interpreting this is that this is saying that this number, a squared, is even, because it's saying that a squared is 2 times some other integer. And I know that b squared is an integer because by definition of the rational numbers, that this b was an integer. And then you have closure of integers are closed under multiplication, okay? Anyways, you don't need to know all that fancy stuff. You can just play with this and it does make sense, okay? Anyways, you could also say that, oh, if a squared is even, this implies that a is even, okay? And this is, you could think of this as like a lemma, right? That basically if you have this perfect square a squared that's even, then that implies that its base, the square root, a is even, okay? Try proving that as an exercise, or you can just play with some perfect squares like this, some even perfect squares, and see, okay? All right, and I'm putting this on the side because you're gonna see why. Okay, so a is even. By definition, that means that a can be expressed as 2 times some other integer m, or for some n and z. And what I'm going to do now is I'm going to make a substitution into this equation. That's why I wrote it on the side. If a is equal to 2m, then I can substitute that here. And then this implies that 2b squared is equal to 2m squared. And then you simplify the right-hand side and you get that 4m squared is equal to 2b squared. And then you divide both sides by 2, and then you're going to get that b squared is equal to 2m squared. And then when you look at this carefully, this can be interpreted as saying that this number b squared is also even. Okay, and then by the same argument that if b squared is even, then it's square root b, right? This says that b is even. Oh, sorry. Yeah, this says that, so I should say this, a squared. So right here, a squared is even. A squared is even, which implies that a is even, right? And then here, same thing. So b squared is even, which implies that b is even. Okay, and this is the contradiction, right? The contradiction, like I said before, is that a and b have no common factors, but in this this logical sequence is a little sloppy, but hopefully you can follow along with what I'm saying, right? That a and b, they have a common factor of 2 by definition of even. Okay, so hopefully that makes sense. And then to finish this, you can use this thunderbolt thing. Okay, so yeah, this can't happen. So basically, that you cannot, that when you assume that square root of 2 is rational, you're going to get this weird hiccup. Okay, cool. Once again, it's been a hot minute since I did this kind of math, but if you have any questions or something's not clear, please message. Oh, also want to say that you could make this more rigorous if anyone taking like number theory and stuff. Another way of saying no common factors is using something called the GCD. So you could say the GCD of a comma b is equal to 1. Just those, it might be a small subset of the audience that has taken the number theory, something like that. Okay, so yeah. Okay, cool. All right, that's it. All right, guys. Good luck and peace out.